Alright, here's a pretty straightforward and kind of interesting exercise. So let's call the set L. So L will be the set of transformations of this type. And I'm going to write them as functions, so like f of x equals ax plus b. But instead of using f, I'll use probably Greek letters. So, okay. And by the way, what does this L stand for? We must prove L consists of bijections such that one is an L and for every single alpha and beta in L, both alpha beta and alpha inverse are in L. There's no particular reason why I chose alpha inverse instead of beta inverse. Basically what it is what you want to prove is that for all alpha and beta, the product alpha beta is an L. And for all alpha in L, alpha inverse is an L. And this just reduces the notation. So let's see here, what else? Oh, just remember that this we discussed in the chapter. This is sufficient for proving that a subset of transformations that a set of transformations is a transformation group. Okay, so let's see here. The map 1 given by 1x equals x is in L. That's because that's when a equals 1 and b equals 0. See here. So there's that. If alpha is an L, and if, let's say, alpha of x is equal to ax plus b, then since a is non-zero, because that's by assumption of things in L, let b of x equal, what is it? We want it to be x minus b. If you work out what you want to happen, you want this to be x minus b over a, which we could write as in a form that's a little easier to work with, or that looks like this thing up here. I'm going to write this as a inverse x minus b a inverse. And then b is also an L because a is non-zero, so you can invert it, and its inverse is non-zero. So let's see here, b is an L. And alpha beta of x, remember this is alpha composed with beta, because these are transformations, and so your group operation is composition. So what is this? This is just alpha of beta x, so this would be a of, and then beta x, and beta x we know to be x minus b over a, and this is plus b. So hey, this works out really nice because this gives us x minus b plus b, which is just x. So alpha beta equals 1. And so beta is equal to alpha inverse lives in L. Now note that this also confirms that alpha is biject. I forget what there's like rules for how hyphens work, but I don't think I've learned them in since grade school. So, and I probably didn't learn them well. So, I'm going to guess that this works. Probably doesn't. Whatever. Yeah, this confirms that alpha is bijective, because you know that if you have a function alpha and a function beta, and if you compose the two and get the identity map, then those two things must be bijections. That's just basic theory of functions. You can prove that using very elementary techniques. So let's see here. Well, at least this is on the sets where they're defined, and of course they're defined on G, and so we're good. So they're bijections on G. So that's a bijection. So lastly, we want to make sure that you can add elements, and by add I mean in this group L, or in this set L. Wait, why am I calling it L? Because they're called G in the problem. For some reason, I thought that, I don't know, like maybe they meant G to be all transformation. Wait. Yeah, I don't know what I was thinking. But let's just change these all to G's now. But I thought I had to give it a name, and I was like, well, these are lines, so we'll call them L. But now we'll call them what it's called. Okay, so lastly, if alpha and beta are in G, and alpha x we'll say is ax plus b, beta x equals cx plus d, then alpha beta x equals a of, and here we're going to plug in the cx plus d plus b, and so this becomes acx plus ad plus b. A and c are non-zero, so AC is non-zero. Thus, alpha beta is in G, hence G is a transformation group. And there we go. This completes the proof.